Pre-Calculus Chapter 1, Section 3. We're going to continue learning about functions and also about their graphs. So let's talk about intervals on which functions increase, decrease, or are constant. So when you have a graph of a function, you read it like a book. You're going to look at it left to right. And as you follow the curve of the function, you're going to notice if your eyes are being drawn upward, being drawn downward, or staying the same. We're also going to notice where the graph switches directions. So we're going to state the intervals on which the given function is increasing, decreasing, or constant. So I'm looking at the graph left to right, and I notice the graph increases until I get to where x is -1, and then it switches directions. My eyes are drawn downward, and then it switches directions again where x is 1. So first I'm going to talk about the interval where it was first increasing. That's where the x's would continue to -infinity up to -1. So we can write that in interval notation. When you're writing the interval of an increasing, decreasing, or constant description, we use a curved parentheses. So now it's decreasing from where x is -1 to where x is 1. Your eyes are drawn downward. And then finally, if you follow the curve the rest of the way, it increases again from -1. And then if the graph space were bigger, it would just continue going, so up to positive infinity. So we're talking about the intervals for the x value or the domain. Example 2. Now this is what we call a piecewise function, and we'll talk about that more in a minute. So we're still going to read it left to right and notice where our eyes switch directions. So first our eyes are drawn downward, and then at where x is 3, they're drawn upward, and then where x is 5, they just stay on the same level. So we can say that the interval the graph is increasing is where x is 3 up to where x is 5. Where the graph is decreasing is where x is 0 up to where x is 3. And then finally it's constant from where x is 5 through where x is 7. Notice the graph has an endpoint, so we don't say that the interval ends at infinity. Example 3, we're going to talk about and locate relative maxima or minima. These are the hills and valleys in graphs of functions where the curve reaches a maximum or a minimum value. So we can see that this has a point, a curve, above where x is -1, that is a little hill, and then a point below where x is +1, that is a little valley. So we say that this graph has a relative maximum where x equals -1, and a relative minimum where x is +1. We can also describe functions as being even or odd. So the function f is an even function if the right side of the equation does not change if x is replaced with -x. Also, if you're looking at the graph of an even function is symmetric with respect to the y-axis. A function f is said to be odd if every term on the right side of the equation changes its sign if x is replaced with -x. Also, by the graph, an odd function is symmetric with respect to the origin. So let's look at functions by their equations. So A, we have a function of a quintic. Let's replace the x with -x and see what happens with our signs. So -x to the 5th power is -x to the 5th. So that sign changed, but the sign for 1 remained. So that means that this function is classified as neither odd nor even. So B, let's plug in -x for x. -x squared is +x squared, so that sign did not change. However, the sign of 2x does change. So this function is also neither. Now for C, let's plug in -x. So we'll have -x to the 4th minus -x squared. So negative to the 4th power is positive, and to the 2nd power is positive. So when we replaced x with negative x, neither sign changed, so that's an indication that this is what we call an even function. And then finally, negative x to the third power will be negative x to the third plus x. So in this equation, both signs switched. Positive became negative, negative became positive. So that fits the definition of an odd function. Now let's take a look at the graph. So we're looking at, if it's even, it will be symmetric over the y-axis. If it's odd, it will be symmetric with respect to the origin. And then if it's neither of those, then we classify it as neither odd or even. So we've got the graph of a rational in our first graph on the left. And if I imagine it, if I flip it over the y-axis, it does not match up. But if I flip it over the origin, it does match up with pieces on the other side. So that means it is symmetric about the origin. So this is an odd function. Now look at the parabola in the middle graph. If I imagine that flipped over the y-axis, it would line up. So it is symmetric with the y-axis. So this is an even function. And then finally, this looks like a cubic function to me. Last one on the right, if I flip it in my mind over the y-axis, there's nothing to match up, and nor the origin. So this one is not symmetric with the y-axis or origin, and it would be classified as neither. Let's talk about a new type of function. It's called a piecewise function. I mentioned it earlier. And the name pretty much describes what's happening. It's a function that's defined by two or more equations over a specified domain, and it's called piecewise. There are a couple pieces. So here's a good example of a piecewise function, c of t. So c of t will equal 20 if t is less than or equal to 6 or greater than or equal to 0. But c of t will equal 20 plus 4 times t minus 6 if t is greater than 6. So see, it has two different parts over two different domains. So let's find c of 4. So we need to look at our criteria for t. And so I look at the first inequality, and that's where 4 would lie. So that means c of 4, we use the first piece of the function, it would equal 20. Now c of 8 is contained in the interval t is greater than 6. So I use the second piece to evaluate this. So I'm going to plug in 8 for t. So 20 plus 4 times 2 will be 28. Now c of 0. So for c of 0, 0 falls in the first inequality. So we use the first piece of the function, and it just equals 20. So c of 0 will equal 20. c of negative 10 is not a part of either of those inequalities. And so that means that this function is undefined when t would equal negative 10. Here's how you graph a piecewise function. So you look at the criteria and then look at what the two or more pieces are. So f of x equals 3, this is a constant, and so it'll be just a line. F of x equals x minus 2. That will be a slanted line. So I'm going to start, and I'm just going to use my table. First I'll draw my xy axis. So I start my table where my interval starts at negative 1. And so my y value just equals 3. And then I'll just do a second value. So I pick a value that's less than negative 1, negative 5, and it will still equal 3. So that will just be a line that extends off in the negative direction. Now I'm going to start my table for my second piece at negative 1. So if I plug in negative 1 minus 2 is negative 3. And then I'm going to pick a value that's greater than negative 1, so I pick 5. 5 minus 2 is 3. When I graph that first point, I do an open circle because it goes up to but doesn't quite include negative 1. And so now we have the graph of that piecewise function. This is a different concept. It's called the difference quotient of a function. So if you look at it, you can see that it is a quotient, it's a fraction, and that there is a difference involved. So it's a difference between f of x plus h and f of x. And that's all divided by that difference between x, which is h. So this is called the difference quotient. This is a formula also for the slope of a secant line. That's a line that touches a curve at 2 points. Let me show you an example. So here we have the graph of a quadratic, a parabola curve, and then there is a secant line drawn through it. And so we have the point x and f of x, and then x plus h and f of x plus h. So remember that slope equals the difference in y values. So our y values are f of x plus h and f of x. So see how that's the difference on top minus the difference in x's. X plus h minus x would simplify to h. So let's find the difference quotient of f of x equals negative 2x squared plus x plus 5. So the first thing we're going to do is plug in the expression x plus 8 for x. So we'll have negative 2 times x plus h squared plus x plus h plus 5. So now we just have some simplifying to do. So I'm going to square x plus h, which gives me x squared plus 2xh plus h squared. And then I'm going to drop my parentheses in my x plus h. Now I'm going to distribute my negative 2. And then finally I'm going to combine like terms. And this is the first piece. Well, actually, there are none to combine. Now I go ahead and do the whole formula. So I take f of x plus h, which is this big expression, and then I'm going to subtract f of x, which is negative 2x plus x plus 5, all divided by h. Now I'm going to distribute my negative after I rewrite my first expression. So that'll become positive 2x squared minus x minus 5 all over h. I'll combine like terms. And what I have left is negative xh minus 2h squared plus h. I notice that I can divide an h term out of everything, so I end up with negative 4x minus 2h plus 1. And then I just go ahead and give a domain restriction that h cannot equal 0. That concludes the notes for Chapter 1, Section 3.